Thank you for having me today and the very kind introduction. So I'm Wan Si. I'm here to represent the Electrochemical Safety Research Institute, or ESRI, which is under the UL Research Institutes. And the title of my talk today is Materials Characterization Methods for Battery Applications. So a quick outline of what I'll be talking about today. So I'll give a brief introduction of what UL is, and then I'll go into the materials characterization and some QA/QC techniques that we are trying to get into our labs right now. So for more information, right now we're trying to build out our labs. We just had a major round of funding that came in. So we are now starting to build out our labs, increasing capabilities, hiring more people. So we're in the process of getting some of the tools in, and I'll be presenting some of the tools that we think are most important to us that are coming in or in the process of being acquired. I'll quickly end with some projects and acknowledgements as well. ESRI is part of UL. UL is separated into 3 different organizations. So there is the ULRI, which ESRI is under. We have UL Standards and Engagement, and we have UL Solutions. So we are 3 organizations, but we have one shared mission, which is on safety science. So we're working for a safer world. So what is safety science? Safety science is a multidisciplinary approach that engages the ingenuity of top minds across scientific fields to engineer a safer and more sustainable world in which every individual can thrive. And this brings us into ESRI. So we are the Electrochemical Safety Research Institute, and we are advancing safer energy storage through science. So just some quick notes about what ESRI is. So we are a part of the UL Research Institutes. It's a not-for-profit organization, and we have about over 100 years of expertise in safety science. So the team is working to advance safer energy storage, including lithium-ion batteries and other renewable energy technologies. And we are currently based in Houston, Texas. Oh, sorry. Thanks. So a slide to just summarize the work that we do. So part of what we do is to identify what the issues are, and we're currently seeing increasing numbers of battery safety related incidents in consumer goods. And this is not just dangerous to consumers, but also to especially first responders. So what we do is to conduct objective investigations, so to have independent research on performance, for the performance and safety of existing and emerging energy storage technologies. And finally, it's most important to say how to resolve the issues, so to share the knowledge for the greater good, to disseminate the scientific information to the community, to the government, public sector, as well as the public. So there are 4 pillars of ESRI. So we have safety research, simulation modeling, outreach and standards. And for me, I belong to the Novel Materials and New Energy Forms team. So I'm here to talk a little bit about how we're setting up our labs and some of the projects that we have. So since this is the manufacturing section of the session today, I thought to put up, what is the manufacturing process that we have currently. So we typically start with materials, synthesis. Go back. Okay, there you go. So we start with material synthesis. So this is not just mining of materials, but also making sure that the materials become active materials that we can put in our battery slurry. And after that, we do a slurry mix. So this is when we have a recipe for our electrode, and we can put all the active materials in different compositions into a mix. And then we do a coating and drying. So I put here as a painter, because if you don't know and you're making electrodes, you're actually making conductive inks, so conductive paints. So it's essentially a lot of the technology that we're using today comes from the paint industry. So you're all painters over here. And then the next step is to calender and slit, to densify the electrodes and then cut them down into the shape that we want, perform the cell build, have electrochemical testing, and of course, various testing from formation to cycling, abusive testing, and then of course to perform a cell teardown, not just to investigate, what happens during testing, but also relates to recycling of the batteries and then going back to material synthesis. So hopefully going forward, this is the way that we have a closed loop system. So let's move into some of the materials characterization methods that we require during the whole cell manufacturing process. So on the right here, this is a schematic that shows various different materials characterization techniques. And there are so many, so how do we choose what we need? So typically what we want to understand is, for example, the crystallinity of your material, particle size, elemental composition, surface morphology, bulk properties, thermal properties, and any gaseous product that is released during battery cycling. So how do we apply all these toward batteries? So let's start with the first one, which is XRD. So I know there have been good examples in the talks today. So this is just one of the examples to show, why XRD is so important. Majority of battery materials are crystalline solids. Of course, not all of them are, but majority are crystalline solids. So XRD is a great technique that can provide us with the crystalline properties of the materials, particle size, composition, purity, and some even understanding the microstrains within the particles. So on the right here, this is an example of an in situ study on hexagonal NMC622. So this study, they wanted to look at how the material is cycling beyond 100 cycles, and they did it within 2 voltage ranges from 3 to 4.3 volts and then 3 to 4.7 volts. And so when we're looking at the lower voltage range, it starts with a H1 NMC phase, but on charge, it goes into H1, H2 mixed phases, as you can see here. And this is reversible, not just in the first 2 cycles, but also up to beyond 100 cycles. However, when we're looking at a wider voltage window, the authors found that it starts with an H1 phase, but it goes into a H3 phase with additional cycling to higher voltages. And with further cycling, it actually goes back to what we see for the lower voltage windows. And so it goes into H1, H2 mixed phases. So XRD is a good tool for us to see, what's happening with our active material. And with the authors also found that with extended cycling, there is increase in crystalline microstrains. So this is something that you can see when doing some Rydberg refinements. And this is linked to particle disintegration and capacity fade. So another technique that we're interested in is optical microscopy. So it's a good visualization tool. So it's nice to know that, from XRD, your material is cycling, but, can we see what's happening? So because a lot of battery materials are micron-sized particles, so optical microscopy is a good tool with a matching wavelength. So it provides information on surface morphology, particle size, composition, and on the right here, this is an example of an in operando study. So they use a Keon's optical microscope over here, and it's paired with an L-cell optical window. So as I mentioned, it's a good tool to visualize the lithium plating and stripping, and there is a nice little video over here that I can play. So the authors, they use a current density of 2 milliamp per cm square, and with charging, you can see that there is this front that moves with charging, and yeah, it's really a good tool to see, what's happening in your batteries. And the authors found that if you have a relaxation or a rest step, that can help with fast charging to allow the battery to relax a little before discharging. And similarly on discharge, you can see that the front moves in the opposite direction. So a very good visualization tool. So other than looking at the electrode, there are other parts of the cell manufacturing process that we can also use optical microscopy for. So an example here is the welding during cell builds. So I just mentioned quickly, cell build of the cell. So there are several things that go into a cell build. So it includes vacuum drying, stacking of the electrodes, welding of the tabs to the current collector, and then enclosing them in some sort of form, be it mylar for the pouches or a casing for the cylindricals or the prismatic format. So why is this important? Is because the welds is where is the contact pathway for charge and discharge. So weld points are very important, where it's the point where you're actually charging and discharging the cell. So it's important to look at how do we optimize the weld conditions through the ultrasonic welder that we use. So over here, the authors for this paper, they found that this is an example of a good weld, and they found that there is microstructure and material flow to form a layered bond during the welding process. So you can see here that some examples of how the weld is good is because there's a wavy interface mixing layer. There are some clinching of materials that you can see, and this wave-like interface of the microbonds. Something else that we can couple with the optical microscope is to couple it with element analysis, so that can provide composition as well. So you can actually see if how the interface is looking, how the materials are mixing at the weld points. So a very complementary method to this is SEM, scanning electron microscopy, which is coupled with energy dispersive X-ray spectroscopy, EDX. So as I mentioned, majority of battery materials are micron in size, but there are certain, we still use some nanoparticles, for example, CNTs. Some of the processes that we are interested in, for example, the SEI growth, that's also nano size, so we need another technique to look at these particles. So EDX is SEM is a great way to look at it. So similarly, it provides information on surface morphology, particle size, composition, and really is a really good visualization tool. So on the right here, this is some in-house unpublished data that we've done on commercial batteries. So we did a teardown of the BAK 21700 cylindrical cells. And you can see that we perform SEM on the anode, the cathode, and we can see some elemental composition coming from the anode and cathode. And it's also interesting to look at the separator. You can see how porous the separator is. So as mentioned, it's really complementary to optical microscopy. So some of the materials can be used on SEM, needs to be conducting because you're using electrons. And some of the things, for example, the polymers are not very conducting. So of course, you can try to coat with either platinum or gold, but sometimes it's also complementary just to look at it using the optical microscope. So something else, another technique that we can use for SEI studies is Fourier transform infrared spectroscopy, FTIR. So this gives us information regarding the organic or organometallic side products on the SEI layer. So similarly, this is data obtained in-house from the commercial batteries of the BAK 21700 teardown. So I would like to say that we are building out our labs, so you can see it's not the best of data. This is not publishable data. You can see how messy the background is. So we are in the process of trying to ensure that the equipment is well set up, that any moisture or background subtraction that we do is better. So yeah, pardon how it looks right now, but we are trying to make sure that is this because of the equipment or is this because of our samples? But we can have some preliminary results still. So we see some signature from the cathode and the separator as highlighted in red and blue here. That's pretty much the signatures that we observe. However, a deeper analysis is required for the anode. So on the anode side, we typically see a peak at about 1367, which is the sp2 graphite vibration mode. But we don't really see it here, so we need to do some analysis that why do we not see it here? Is the graphite somewhat not pure, or is there something going on the surface? So some of other techniques that we can pair with are like SPS or TOF sims to really understand the species and concentration. So one thing that we are very interested in is to perform in situ studies. So in this way, we can look at how the SEI layer is growing with FTIR, with cycling. And this paper here has a very good reference on how to do it. So we're trying to get this technique in-house. Something else that we're interested in is thermal properties. And we can use ThermoGravimetric analysis, TGA with differential scanning calorimetry, DSC, to find out more information. So this is a gram scale instrumentation method and can provide information for the different battery materials or different components. So other than thermal properties, we can understand the purity of the phases, any phase change, any mass loss. So on the right here, this is the data obtained from this paper over here. So they did an ex situ analysis of commercial batteries with at various SOCs. So they looked at different chemistries, LCO, LFP, and NCA. So on the right here, on the DSC that's tagged with TGA, they performed it on the separators. And you can see that the separator decomposes above 100 degrees Celsius, and there is mass loss that comes with that decomposition. And so for the authors, this is the summary of the findings. So they found that for LCO, there is a stepwise decomposition that happens, whereas for NCA over here, it has a very sudden decomposition when you heat out the sample. And for LFP, it's the most stable because of the cathode, and the decomposition occurs above 500 degrees Celsius. So this is on the smaller scale. So we can also use, we can also find out thermal properties on the larger scale as well. So another thing that we can do is accelerating rate calorimetry, the ARC testing method. So it's not just for individual battery components, but we can also test cells, packs, modules. So really, it's a really good tool. As you can see here, this is a chamber. And we can understand the interactions of the different components during thermal runaway. So it can be run in the isothermal or the adiabatic modes. It's also an in-operando study, so you can actually track the voltage of the cell as you're performing the ARC testing. Over here, the data is from this study on comparing pouch cells with varying separators. So on the right here, this is the example of the ARC data that's obtained for the modified graphene polydopamine coated separator. And the authors found that these are conclusions that with the graphene doping, the temperature, the decomposition temperature of the cell is much higher than as compared to standard electrolyte, cellulose trilayer, and standard, just because of it's the best performing one. So finally, we're also interested in gas chromatography, mass spectroscopy, GCMS. As we know, there are, so there are various different gaseous side products that can form in the cell during cycling, from formation, aging, or thermal runaway. You can see here, this is an example of a spicy cell. And so, we want to understand what are the gases that are released. So GCMS can be coupled with other techniques. For example, FTIR, we can understand the formation process or how the SEI layer is being formed. It can be coupled with ARC testing as well for thermal runaways. So on the right here, this is some data from a study on cylindrical cells with different aging conditions, and you can see that it's overcharged, aged, and unaged cell. You can see that at different times, different gases are released and different amounts of gases are released. And then that way we can understand how safe the battery is when it goes into thermal runaway, what are the gases that are produced. Let's see. So I've gone through more or less the materials characterization parts, but as I mentioned, during the battery manufacturing process, there are other things that we need to track as well. So QA/QC, quality assurance, and quality control is very important during the manufacturing process. So the first one that's really important is rheology. So especially the rheology of the electrode slurry. So there is a relation between coating methods and viscosity ranges as shown on this table on the right. So you need to, if your slurry is of a certain viscosity range, it means that you need a certain coating method to ensure that it's really a good coating. So of course, Dr. blade is used for typically small scale trials, similar to a knife over roll. But typically, as we are scaling out, we're looking at the slot die, a comma or reverse comma, Gravier coating. And if you're not well matched, it means that you may have some coating defects, and some coating defects are examples are shown here. So I think ribbing is something that's very common, but there are other defects that can occur as well. So for the rheometer, the data that it provides is a viscosity against shear rate. So it's a really important metric to track during the slurry mixing and coating process. So I'm sure everyone has some experience where, if you change your recipe, if you change an active material, your slurry doesn't come out the way that you want it. So it's a very important metric to track, and you need to do some rheology measurements every time you do, when you change your slurry mixing process. And another thing that's really important is the amount of water in your sample, so moisture analysis. There is a relationship between poor electrochemical performance with the presence of trace water. So looking at the literature, typically between 200 to 300 ppm, that's where it's sort of the sweet spot where you still have good electrochemical performance. Anything above that, you start to see some poor performance, but anything below that, your electrode starts to be, might be very easily for your electrode to delaminate. So this study over here, they looked at the water content at various battery manufacturing processes, and they had some recommendation on best practices. So you can see that they measured the different anode, cathode, and separator across the different manufacturing processes. And we probably all know this, that we do need the dry rooms, especially for, I think, the cell stacking as well as the electrolyte filling and sealing. Of course, anode, we are sometimes using water-based slurry anyway, so this can be offloaded from the dry rooms. But majority, the dry room conditions are more or less recommended. So the calorimetric Fisher moisture analyzer can help to monitor up to about 1,000 ppm of water per the ASTM standard. So it's also an important metric to track, especially the individual battery components during the entire cell build process. So just as a quick summary for this part, we looked at the cell manufacturing process. We know the material characterization that's required, also some QA/QC. But I'm also interested to see how this changes in the future. As I mentioned, a lot of the technologies now that we're using comes from the paint industry. It works for, current lithium-ion technologies. But as we move on to, solid-state batteries, as we remove solvents from our manufacturing process, when we use additive manufacturing or any other future battery chemistries, if we use robots and automation, how does this change? And of course, we need to pivot. How do we do QA/QC? What's the best materials characterization method? So I am interested to see how it changes and how we pivot in order to move with the times. So I'll quickly talk about some of the projects that we have. We have a project with magnesium ion separator with Professor Yao, who's in the audience today. I think he'll give a talk tomorrow as well from University of Houston. We have a project with Professor Balaya at NUS on new lithium-ion battery materials. So this is on an LTO and a LMFP, which is manganese substituted LFP. And we're trying to make 18650s, so a very interesting project. We have a solid-state battery project with Professor Shen in University of Houston. So he is an optical microscope specialist, so very interesting to see how the batteries are changing with charge and discharge. We also have another project with Professor Shen on hydrogen generation research, so trying to see what a new catalyst can be to produce hydrogen. There is also a project with Professor Protesek from Case Western. So it's on electrolyte additives. So we're looking at flame retardant ions, fryons. So it's either a phosphorus-based or a boron-based anode, anion that can be added into your electrolyte in order to reduce how fast the electrolyte goes out in flames. Finally, we're also starting an internal reference library. So of course, we are the new novel materials group, but we need to have a baseline comparison when we, when we call about safety. What do you mean? How do you compare it to what else is? So we're trying to start an internal reference library for us as a baseline comparison. Some interesting upcoming projects. So we have an EVs for All program with ARPA-E coming up. So we're going to partner with Sandia, Purdue, and UMD. So this is a 2.5 years program to work with various different collaborators. So very exciting. You can see that it's a lot of different partners. So it's going to be a big project. So both looking forward to it, but also, we understand there'll be challenges working with ARPA-E. But that's coming in October. So next week. We also have a CARES program with Professor Mukherjee from Purdue University. So this project is to innovate, connect, consolidate research toward advancing the frontier of safety science in energy storage. So we have safety as one of our goals, and to use computing, experimental methods, partnering with other groups to disseminate, to research and disseminate information. So just quickly to say, what is the vision for the Novel Materials and New Energy Forms team? We are part of UL, so safety is a big part of what we do. The design of experiments should have a proactive safety objective in mind. We're interested in science, so to investigate novel chemistries for energy storage and conversion. And we're also interested in the engineering. So as I mentioned, processes are going to change with different chemistries that we're going to use. So to develop new methods for cell fabrication process. And I also mentioned that, we're in the process of really expanding our research in terms of capability, our team. So yeah, this is a really good time to set this vision and goals. So to acknowledge the team at the novel materials side, so we have Migo, Valaba, and Bisi, and also the other members of ESRI as well. So we are about 15 people right now, and we had 7 people just start this year alone. So that's the rate that we're expanding. So something else that we do is, to, as I mentioned, educate the public. So we have this safety campaign called Be Nice to Your Device. It's really to encourage young people to start, thinking about recycling. So feel free to go to this website to learn more on how you can recycle your batteries, be it lithium-ion or not. Finally, I want to thank you for your attention. And as I mentioned, we are expanding, so there are some career opportunities. Feel free to go to our website or, just talk to me, not a problem as well. So thank you so much, and please let me know if you have any questions.